So thank you for having me. Thank you for coming. So I want to show you our package Neuroblox.jl, actually also Neuroblox, the GUI, Neuroblox brain circuits. Let me just introduce the group that is working on it. So these are the people who came up sort of with this idea. This is my wife over here. So we're both at Stony Brook University. Then we have a team at MIT, so Alan Edelman and Chris is here. At MIT CSAIL. Then we have a collaborator at MIT in neuroscience, Earl Miller, and then we're collaborating also with Rick Granger at Dartmouth, and he's a computational neuroscientist. So we're interested in human brains, but what we're doing is any model that we are creating, we're also validating on monkeys because they, the problem is that we are not mice, so we have to work with brains that are close enough to humans. We also have two collaborators, clinical collaborators at McLean Psychiatry and MGH Neurosurgery. We're multi-scale, multimodal, multi-system simulations. We're modular, biomimetic, and intuitive, and we hope to be a community-based modeling platform. I will talk later about this. So this is our team, programmer teams. We have several staff scientists. We have a few PhD students. We are lucky to have actually a dedicated graphic designer that works on this team. And we have a GUI developer, and we just added 2 beta testers. They're actually both from MGH Neurosurgery. And our code base is growing. But let me first tell you the motivation of our work and why we started Neuroblox.jl. In general, when you look at brain-based disorders, there's a consensus that they work pretty much exactly like all other diseases because they're based on circuit dysregulation. And I just wanted to give you an example. This is a very commonly known regulation, glucose-insulin regulation. So if you look at a healthy person, has relatively stable blood sugar, but if you have a disease that affects the insulin, then it's more fluctuating. And the circuit is very simple, actually, right? So if you have blood glucose, if the blood glucose is too high, or if you anticipate eating sugar or something like this, right, that the pancreas creates insulin, the insulin interacts with the cells will take up glucose from the blood, and you get back to the level that you want, right? There's actually 2 places where this circuit can break. One is at this stage where you make insulin, right? And this is actually type 1 diabetes. Type 1 diabetes, you can't make insulin, right? Therefore, the circuit is broken, and you can't regulate blood sugar. That's why you have to inject insulin. It can also break here, where the connection between insulin and the cells are broken, right? And this is actually called type 2 diabetes. And that means that the cells don't react to insulin and therefore not taking up the glucose, and therefore the regulation is broken. Now, the current state of neuroimaging and neuroscience, to a certain extent, is so that when you do neuroimaging, you typically look at the brain and you look at activation areas, right? And you relate these activations to like tasks or even diseases. And all you can do essentially with this kind of data, you can essentially connect dots. You can say these are correlated, let's say 2 regions are correlated. And at best, you can actually establish directed connections between. So you can establish causal relationships between these nodes. But what I wanted to point out that these things are actually not circuits, right? Not yet circuits. And that's why I think we had to do what we wanted to do. I just also wanted to give you a control circuit in the brain. This is actually, my wife has been working on this for many decades. You can see the symbols more remind you of an electric or control circuit. I don't want to get into details, but it is essentially a circuit that is implicated in anxiety disorders. It's actually the circuit that controls your threat assessment, right? You look at something, you say, is it a threat or not? And it can also be broken in two places. One, if you are a hyper responder, if you're anxious, then you're always you have false positive messages, right? Something that is not a threat is a threat, and therefore you're anxious. There's another place where this thing can break, and these are hyper responders, and they have false negative. So you see a threat, but you think it's not a threat, right? And they are living very dangerous lives. So very similar to the glucose regulation, you can think about the brain. So now the question is, how do we actually go from these control circuit things to actually brains? And the big question that we have to ask ourselves, so what are really the computational primitives in the brain circuits? It's pretty easy when you look at electronics. Electronics, we have resistors, we have capacitors, right? We could have transistors, we could make all sorts of things. But what is the equivalence in the brain? I'm showing you one example. This is called the winner-takes-all circuit. And it's essentially a multimodal switch, or maybe a filter. My wife likes to call it a filter. But the idea of the winner-takes-all circuit is that you have a bunch of excitatory neurons, and you have one inhibitory neuron, and you have inputs, and the neuron that gets the most inputs shuts down the other neurons, right? So there's only one active neuron in this circuit, microcircuit, and that's essentially to make decisions, right? You can either the first one, or the second one, or the third one, or the fourth one, and this is sort of like a basic circuit. But we want to extend the library of computational primitives. Okay, the next problem is multiscale. If you think about it, I mean, if you have a brain disorder, right, it manifests in behavior, let's say, right, addiction, and so on. So at the scale that we can measure the human brain is, let's say, fMRI or EEG. That's very coarse, right? So I think typically voxel sizes in fMRI are like 1 millimeter, maybe 2 millimeters, and so on. EEG, you only have access to the scalp. There are finer measurements in monkeys. You can put electrodes in their brain. You can also, in humans, deep brain stimulation, you can actually, during the surgery, you can get very, very good measurement. That's why we collaborate with these people. But then ultimately, if you think about it, the molecules are the ones that we are interested in, right? So if you want to treat a brain disorder, then you give drugs, and the drugs will act on the bottom layer of this hierarchy, right? And on the right, actually, we show essentially you go from cellular, molecular, to individual neurons, right, to neuron assemblies, and only then on top you see what we see in neuroimaging. So we have to have models that are completely multiscale, that are hierarchical multiscale, from the bottom to the top. Okay, and then the other thing is we also need to have a way of comparing models. We have to integrate them, we have to share them. So model comparison, right? So we want to know, you have a model for an amygdala, and you have one, and we want to see which one is better. Integration is a big problem in neuroscience, computational neuroscience. Somebody has a model, it doesn't integrate with any other model. If you have an amygdala, I have a thalamus, we can't talk to each other. And sharing, there's a nice quote about sharing of neuroscientists. Okay, so this is why we started Neuroblox.jl. Neuroblox.jl is built on modeling toolkits, so we do everything in symbolics. So what I wanted to do is, since most of you are probably not computational neuroscientists, also to speak a little bit about our experience to building big systems, right, with modeling toolkit and how to integrate lots of differential equations and parameter sharing and so on. So I will show some code. Let's start with a very, very simple computational primitive. So this is a very common thing that people in computational neuroscience do. We have 10 to the 11 neurons in a brain, right? That's impossible to simulate, even if Moore's law continues. So what people said is, let's take a cluster of neurons, thousands of neurons maybe, and ask what is the average dynamic behavior of thousands of neurons. And typically it involves excitatory, inhibitory neurons to go back and forth. And you essentially end up with a mean field approach to neuroscience. You get essentially a differential equation. So one of the famous neural mass models is the Jensen-Ritt model. And this is essentially a coupled differential equation. So you have X, which is the dynamics of the excitation of the neural activity, and Y is some latent state. Okay? And then what we actually do is we pack that into a block, right? We create a struct, which we call Jensen-Ritt block. And then we define essentially outputs and the ODE system. And the ODE system is created essentially by writing out the equations, creating an ODE system, saving it. So how do you connect those, right? So by connecting those, you just essentially create all these blocks. And then you can even attach parameters to it. And then you define an adjacency matrix, how to connect all these things, the inputs to the outputs. You create a system, you structurally simplify it, you simulate it. Now, this is so simple that we were actually able, so one of the students came and gave us a paper like on Parkinson's disease, right? It had essentially, I think it has 7 or 8 regions, no 7. I was able to put that into Neuroblox within an hour, and we can actually reproduce the results. Can you imagine, like, you have a scientific paper, you look at the results, and you get instant, essentially, you can test it, you can change your own parameters and so on. So it took me a little longer to make this graph here, over there. The other way of assembling systems, and I like this, by the way, the graph way much better, because it's more intuitive, is to actually assemble ODE systems from graphs. So just imagine you have 2 regions, they're connected in a certain way, you have parameters, you can even have equations in the connections. Essentially create the nodes, you create a directed graph, you add the blocks as vertices, you add the edges, and you call ODE from graph. That's it. You have an ODE system, you simplify it, you simulate it. Now I want to talk to you about superblocks. Superblocks are assemblies of blocks, right? Hierarchical, we want to build things hierarchically. So this is an assembly, this is called the canonical microcircuit. It is essentially 4 different types of neurons that interact in a cortical column. And there are a lot of literature on this. So how do you do this? So now this cortical column has 4 inputs and 4 outputs. You do the same thing. You essentially create another block, like another struct. This time it has symbolic arrays, inputs and outputs. And then you essentially go create the blocks. You add them as vertices, you add all the edges, and then you have to connect the outputs to the outputs of the blocks. That's it. Right? And now you have a struct, you have a block that connects 4 to 4. How do you connect those super blocks? Very simply, again, you create them, you create a graph, you add the super blocks as vertices, and now instead of a single weight, you put a matrix, right? You put an adjacency matrix. So to essentially connect all the inputs to the outputs, right? Or actually the other way around. So if it's an edge, directed edge, you connect the outputs to all the inputs. And again, you call ODE from graph and you have a network. So let me show you an example, what we did last year, essentially to build a huge system that explains something. And so we take the winner-takes-all circuit, it's a super block, 6 inputs, 5 outputs. You connect them into a big system. You can actually, if you connect them together sparsely, that thing behaves essentially like a cortical region, right? We built a visual cortex with this. We built a prefrontal cortex with this. And this is the circuit. So we created essentially a cortical striatal thalamic loop circuit. And this is actually a model for pattern learning. So we actually used monkey data. There's experiments where monkeys learn patterns, right? 2 different types of patterns, and they get better and better at this. And so this is the circuit. It contains 650 neurons and several neural mass models. And it takes about simulation 615 milliseconds for, no, to simulate 615 milliseconds, it takes about 50 seconds using a stiff solver. And this is work by Anand Pathak and Richard Granger. So these are the results. So we validated this. The interesting thing is, after we built it, we actually found features that weren't actually explicitly in the data. So that's really a great news for us. So these are actually the weights that change over time as the learning goes on. I don't think you have to understand everything. Here on the right, essentially, is the behavioral learning. So it starts at 0.5, right? The monkey doesn't know which pattern is the right one, and then it goes almost to 100% because they get rewards. Okay. I wanted to also mention that we now also started putting in stochastic differentiation, stochastic differential equations. These are called stochastic blocks. We used a new feature of Modeling Toolkit that allows you to specify a Brownian noise as at Brownian here. And also we are starting using the new system instead of ODE system, which allows you to then combine SDEs and all sorts of features. The other thing that we just did, actually, and this is something very important, Chris, don't yell at me because it's horrible code, but it works. So we just started, a huge annoyance to us was that we have some models that have 30 parameters, right? So imagine you have a model that has a block that has 30 parameters. You add, let's say, 100 of those together to make a dynamic system. That's 3,000 parameters, right? And most often, these parameters are actually the same between blocks, right? And it actually was very hard for us to get them to get together. And we just solved this actually last week. I tried to make better code, but we will later. But it works. And the way this works is that what you do is when you initialize the block, or the function Jensen-Ridd block, you see these initializer, right? So you see tau is equal to 0.01. But tau could also be a symbolic parameter, right? Rather than a number, it could be a symbolic parameter that we want to share. And the way we do this is we essentially ask each parameter whether it's a number or whether it's a symbol or num. And if it's a num, we change its parent scope. We go one down, which means that on every level we can define parameters and they penetrate through the end to the ODE system. And just to show you how this works, so you create two Jensen-Ridd blocks, right? You create a parameter, put that parameter into the parameter list as the same name, and then you can see at the end, the ODE system has 7 parameters rather than 8, because these two parameters were combined into one. Also incredibly important for parameter fitting, because if we have 3,000 parameters and we take a Jacobian or something like this with respect to 3,000 parameters, we would rather have every parameter that's independent to have a derivative. So that's nice. So these are the collection of blocks that we have. We have lots of neurons. We have Hodgkin-Huxley neurons, integrate fire, leaky integrate, quadratic integrate fire. We have Jensen-Ridd, Wilson-Cohen, pretty much anything that is in the literature. And if you have any wishes, you can contribute them. We have superblocks, canonical microcircuits, winner takes all. We are actually working on a cortical superblock, which means that we will have hundreds of inputs and hundreds of outputs of these things. We also have utility blocks. We can take data, bandpass filter them, then send them to another block, and so on. And then also stimulus blocks, because we need essentially blocks that create data, like, for example, a noisy input or images. I mean, the monkey data are patterns that are shown to the cortical block. Okay, now I want to do a GUI demonstration. One of the things that we always wanted to do is to make this tool available for anybody who doesn't know differential equations, who just wants to look at a model. And the other idea is that, let's say you using Neuroblox for your research, you get a result, you publish the result, then you can essentially save the model as a file. I mean, right now it's a JSON file, but we're working on other formats. And then you can import it into GUI, create essentially the OD system, and then you can change parameters and play around with this. Imagine you have publications that are interactive. Right? We were actually just talking about this, right, with one of the previous speakers. So the GUI was done by Adrian and Daniel initially. He's essentially behind Genie.jl, and we hired another front-end developer for the last year, Wyatt Felt. So this is the GUI. So we have different backgrounds. They don't have a meaning yet. And then down here at the bottom, you have all the blocks that you can use. You just have to click one of these blocks and you can see that they have different parameters. You can change the parameters. You can create another one. And then you can make connections, directed edges. And then you can also choose what neurotransmitters constitute that edge. And you can also make self-connections. Okay. And then we also have superblocks, right? So you can connect superblocks. Superblocks essentially have the number of outputs to inputs written on them. So you can distinguish those. So you can see Janssen-Witt block has only one output, so there's only one. And then 4 back because the CMC has 4. This is, by the way, this is the Parkinson's model, right? That is importable. So this is a 7-region model. And essentially, this parameter changes the frequency of, this is actually what does the tremor in Parkinson's. We can have neurons. You can do a neuron simulation. By increasing the input, you increase the frequency of the spikes. And this is actually a cool feature. So so here you can graphically, this is not actually in software, but it's graphically, you can compress regions. Because if you think about it, if you have 100 regions, you want to pack some away in the corner. Here we can essentially do cortical and subcortical, summarize them. And you can get the latex out of the thing, right? So you just click on it, you get the equations out. We are not there yet that it writes the paper for you, but we're working on it. Okay. Exactly. So right now we're finishing actually parameter fitting. So the idea is that all these models should be able to take data and then fit the parameters to it. Right now we implemented actually what is called DCM, Dynamic Causal Modeling. This is implemented in MATLAB in SPM 12, which is the most common software used in neuroimaging. So anybody in neuroimaging uses SPM 12 or derivatives of it. But the idea of our kind of curve fitting using the same models is that you define a model, build a circuit, define the measurement, right? You say fMRI, EEG, whatever. It extracts essentially what you would measure, right? If this was the neural dynamics, then you essentially give the data, you give the fitting method. So right now we have variational inference, so it's Laplace approximation, but we're also using ADVI, so automatic differential variation inference. And the speed, if you look here, so we have actually 2 versions. We took SPM 12, we translated it into Julia, we get some speed increase, but then if we add AD, we get even more speed increase. And we actually just managed to get the symbolic version to also do AD. So it's the same speed. And here you can see that ADVI is actually better of predicting ground truth than Laplace approximation, which should not be a surprise for anybody. Then the next step is we are finishing reinforcement learning. So I told you there was a whole system on learning. So the idea is that we have a simulation essentially. We run a simulation a certain amount of time. Then we interrupt it with callbacks. Then we involve an agent that looks at the data, looks at the simulations, then changes the parameter to somehow optimize the cost function. And that should be implemented in the GUI very soon. We have it already in code, but it needs to get into GUI. Future directions. So in reinforcement learning, I think we should be finished by October. We also want to implement a more Bayesian parameter fitting for neural data. That also allows you then direct comparison between models, because you can take the ratio of the posteriors. We have not implemented delayed differential equations, but Chris, they just implemented into modeling toolkit. So very, very nice. And Neuroblox GUI is already hosted on JuliaHub, or at least it's very close. You saw it already, I think. Wish lists. My wish list is that we create a domain-specific language for our circuits, so that we can actually share data better. And release of Neuroblox is coming soon. I hope it's intuitive, it's fast, and we're hiring. So if you're interested, talk to me. Okay, and it was funded by the Bazooki Brain Research Fund.